Okay, what we have here before us is the Riemann zeta function and its expression as a product over primes. So the Riemann zeta function, the series right over here, is the prototypical example of a Dirichlet series. And Dirichlet series are series of the form a to the n over n to the s, where an is an arithmetic function, that is a function from the positive integers to complex numbers. And in this case, the Riemann zeta function is the simplest such function with an identically equal to 1. And when the arithmetic function here is multiplicative, meaning that am times an is equal to am n for coprime positive integers m and n, then it has an Euler product representation. But what we are going to do in this video is, first of all, to prove this equation and show that both expressions converge absolutely on the half-plane real part of S greater than 1 and diverges if the real part is less than 1. And also we are going to show that this series right over here is a holomorphic function on this half-plane. And this result will serve as a starting point for our study of Riemann's paper, where he studies the zeta function and where he conjectured the Riemann hypothesis. So let's prove this. So before, first of all, this infinite product right over here, we know that it converges absolutely if and only if this series, which is 1 over p to the s for p over primes, converges absolutely. And we know that 1 over p diverges. That's basically how Euler's proof of the infinitude of primes. And when s is greater than 1, then this converges absolutely. And this series also diverges when s is equal to 1. It's then equal to the famous harmonic series, and it converges absolutely when the real part of s is greater than 1. So when we have absolute convergence of series and products, we know that we can freely rearrange without upsetting the sums. And this expression right over here is really an analytic reformulation of the fundamental theorem of arithmetic, which says that every positive integer can be expressed uniquely as a product of powers of primes. So when we know that both sides converge absolutely for the real part of s greater than 1, then it's quite easy to see why this is true. So if you rewrite the left side like this, so we write the primes 2, 3, 4, 2, 3, 5, 7, and so on. Then, since this thing right over here has absolute value less than 1 because of the real part of s being greater than 1, then it means you can expand each of these as a geometric series like this. Times 1 plus 1 over 3 to the s plus 1 over 3 to the 2s plus 1 over 3 to the 3s and so on, and similarly for every over prime. And now you just multiply out the brackets, the terms in the brackets, and by the fundamental theorem of arithmetic and the absolute convergence of the product and the series, you get exactly the term 1 over n to the s exactly once for every positive integer n. Okay, so that was for this relation. And so notice something. So that's basically connecting this function to the primes, but it doesn't reveal a lot right now. When you extend this function to the entire complex plane, then you get very deep results and hypotheses about the primes. So now we are going to show that this function here, considered as a function of the complex variable s, is holomorphic on the half plane real part of s greater than 1. So we are going to show that this is holomorphic on this half plane right over here. And the way we are going to do this is as follows. So first of all, we know that the uniform limit of holomorphic functions is holomorphic. All right, and so if a sequence of holomorphic function converges uniformly to a holomorphic function on some open set, then this limit is itself holomorphic. However, the condition of the uniform convergence is too strong, and we can have weaker conditions that give the same result. For example, we can't show that this, we don't have to show that the sequence of partial sums of this series converges uniformly on the half plane. We need only show that it converges uniformly on compact subsets of this half plane. So if we are able to show that the sequence of partial sums converges uniformly on compact subsets of this half plane, then it would follow that this function is holomorphic on this half plane. Now that's easy. To show that it converges uniformly on compact subsets of this half plane is easy. But what we are going to do in this video is, in addition, prove how being uniformly convergent on these compact subsets of this half plane makes it holomorphic. So first we show that it converges uniformly on compact subsets of this half plane. So we can equivalently consider every half plane where the real part is greater than or equal to 1 plus epsilon for some positive non-zero epsilon. And then it would follow that this sequence converges uniformly on compact subsets of this half plane. And that's easy. So it's basically, so this thing right over here is less than or equal to the sum of absolute values. And for the absolute values, you can just replace s by its real part. So n to the real part of s. And we know that this thing converges when the real part of s is at least 1 plus epsilon for some non-zero epsilon. And now by the Weierstrass test, so it implies that this series converges uniformly on all compact subsets of this half-plane real part of S greater than 1. But now we are going to show why this implies that this function right over here is holomorphic on real part of S greater than 1. So, first of all, we know that in the finite sum, so each of these summands is holomorphic on the half-plane real part of S greater than 1. So this thing is holomorphic. That's a finite sum. We want to show that the infinite sum is holomorphic. And since it's holomorphic, therefore, if we take any closed contour in the half-plane, so that's a closed contour in the half-plane real part of S greater than 1. Usually people, when there's a closed contour, they like to put this little thing right over here because it's fun to draw, but it doesn't really add anything new, so we can just ignore it. So since this thing is holomorphic, therefore the integral of this with respect to S is equal to 0. And that's because of the Cauchy integral theorem, also known as the Cauchy-Gauss theorem. Right. But now let's consider the limit as k goes to infinity of this integral. Since this C right here is a closed contour, therefore it's a compact subset in this half-plane. Therefore, and since this sum under here, we have shown that it converges uniformly in the half-plane, the real part of S greater than 1. Therefore, we are allowed to interchange the limit and the integral sign. So we can just move the limit outside, we are justified. And when we do this, this thing right over here becomes this. We can take off this limit and it becomes the integral of C of this infinite sum. But since each of these is equal to 0, the limit is also 0, and so this integral is equal to 0. Now, we have shown that this series is uniformly convergent on compact subsets of this plane, so it's uniformly convergent on C, and in particular it's continuous. In fact, it's because the uniform limit of holomorphic functions is continuous. And since its integral is 0 and it's continuous, the sum is continuous, it follows that the sum, this thing, is holomorphic on every compact subset in the plane by Moreira's theorem, which is a sort of partial converse to the Cauchy-Gauss theorem. And so this sum converges uniformly on compact subset of this plane, but it is also holomorphic on this plane. So, okay, so now we have shown holomorphicity of this function on this plane, and that's the starting point for our further study of Riemann's paper, and we've barely scratched the surface.